Today's topic is DFA state minimization algorithm. The algorithm is going to take an arbitrary DFA as input and is going to give the minimal state DFA as output. That is the DFA with the minimal number of states to produce the same language. So here an example pair of DFAs are given, A and B, and both A and B are accepting the same language and hence they are equivalent, and B is the minimal state DFA. The question is, how can we obtain B from A? The answer is, you find the equivalent states Q0 and Q1, you merge it into the new state, and that is how you can do it. Another example, A and B equivalent DFAs generating the same language. B is the minimal DFA. Question is, how can you obtain B from A? The answer is, you find the equivalent states. Here Q2 and Q4 are equivalent, merge them into this state. Then Q1 and Q3 are equivalent, merge them into this state, and then you are getting B. Third example, A and B are equivalent DFAs, where B is the minimal state DFA. The question is, how will you obtain? Again, you find equivalent states, these three are equivalent, merge all of them into a single one. You will get this automaton. Now, the question is, how can one use an algorithm to find whether two states are equivalent or not? And if you find it, then how can you collapse them? These are the two interesting questions. How we can find equivalent states and how we can collapse equivalent states. We are going to answer the first question by finding answer to this question. What is it? How we can find states which are not equivalent. And if you know which pairs of states are not equivalent, then that is enough to see which are equivalent pairs also. So this is the question that we are going to answer first. So how can we find whether two states are equivalent or not? Here a part of the DFA A is given, and the question is, are the states P and Q equivalent? P and Q are two reachable states from the start state. Are these two states equivalent? Suppose they are, assume that they are equivalent. So why we need equivalent state? We can collapse them into or merge them into a single state to reduce the number of states. And now suppose P and Q are equivalent. So what do? You collapse these two into a single state called PQ. And this time I assume that the collapsed state is final. The other case we can consider later. So first consider the collapsed state as final. One of them is final, we made this as final. We can see what will happen if we make this non-final later. Now the question is, are these two equivalent then? If you collapse them, are these equivalent? For that you need to look at the language. From here you know that the path for X is ending in a non-final state and hence is not in the language, and path for Y is ending in a final state and hence in the language. But in the collapsed automaton or the minimal automaton we obtained by collapsing these two, both X and Y are accepted because the X path and Y path ended in a final state. So both accepted, and hence the answer to this question is no. A is not equivalent to B. Now consider the other possibility. You make this a non-final state. Will it help? Try it. In this case, this is the same language of the given machine, not the language, two strings in the language. But here you can see that both X and Y are not in the language of B. Hence, in this case also, A is not equivalent to B. So we can observe that two reachable states P and Q Reachable means P and Q are reachable from the start state. That's it. They are not equivalent when one of them is final and the other one is non-final. It doesn't matter which one is final and which one is non-final. If one of them is final and the other one is non-final, then you can say that the pair of states is non-equivalent. So that is the first point. Remember it for the algorithm. When two states reachable, one of them is final and the other one is non-final, then they cannot be equivalent. We cannot merge them. Consider another case. Here we are asked to find whether the reachable states P and Q are equivalent or not. Different than the previous case. Now both are non-final states. But another situation we can exploit and see whether they are equivalent or not. The situation is this. From P, the path for Z goes to a final state. And from Q, the path for the same string Z goes to a non-final state. This is what is given. So from the given situation, we know that XZ is ending in a final state and hence in the language. YZ ending in a non-final state and hence not in the language. Question is, are P and Q equivalent? Suppose they are. Suppose P and Q are equivalent and look at the string Z. Let Z be this string A1 to AN, a string of length n. Now we can redraw this figure by concretizing this path. This is just an abstract path for Z. Concretizing means A1 to AN will take you to R. See, this is P to R for Z. This is again P to R for Z, but concretely giving the transitions. That's it. Now magic here. Now we assume that P and Q are equivalent. If they are equivalent, we can merge them. Try merging them. So this is the situation. So we merge P and Q into PQ. This is how you can merge. Now the question is the resulting machine a DFA? What is your answer? The answer is no, because you have two transitions for A1. The simple is A1 from here, input simple. For the same input simple A1, two transitions are there from PQ. Hence it is not a DFA. Hence in order to make this a DFA, as a consequential effect of merging P and Q into PQ, we have to merge P1, Q1 as well. So this is the situation now. But we have not solved that problem completely. It is just got transferred into this state. Now here is the non-determinism. Now you need to remove that non-determinism by merging these two states, and you want to continue it till you get into this automaton, where you finally merge the R and T and you are getting this. So now you can rewrite it as no need to remember the intermediate state. You can abstract away. You can say that A1, A2, etc. AN is taking you to RT. And what is A1, A2, etc. AN? It's nothing but Z. Now this is Z. So you obtained a reduced DFA B. Now the question is A and B equivalent? Now you see whether XZ and YZ, what is the status of XZ and YZ in beta, in B. XZ is not accepted because this is a non-final state, and YZ is also not accepted. Hence the language is different because here XZ was in the language, here it is not in the language. Now the only other possibility you can try is this merged state can be made a final state. Okay. Now what about this question? Are A and B equivalent? See what happens for XZ and YZ. Both are accepted in this case. Now the language of A and B are different because at least in this case of YZ, it is not in the language of A, but it is in the language of B. So hence these are non-equivalent. Now the observation that you can make from this is that two reachable states P and Q, both final or non-final, even though we discussed it in terms of two non-final states, it works for two final states as well. So if P and Q are reachable non-final states or reachable final states, they are not equivalent when there exists an input string Z such that the path for Z from P goes to a final state. That is what is represented like this. Path for Z from P goes to a final state, and the path for Z from Q goes to a non-final state. If that is the case, then P and Q cannot be equivalent. So these are the two observations enough for us to derive an algorithm. Just recollect the two observations. The first is that two reachable states P and Q are not equivalent when one of them is final and the other one is non-final. What is the second observation? Two reachable states P and Q, both are final or both are non-final. That is, this condition cannot be applied. Both are final or both are non-final. Are said to be non-equivalent when you can find a string Z such that the path for Z from P goes to a final state and the path for Z from Q goes to a non-final state. Exactly this situation. Then also they are non-equivalent. So these are the two conditions to be satisfied for a pair of states to be non-equivalent. And we can try to combine this to form a single statement like this. So A and B can be combined to get this. And what is the statement? Two reachable states P and Q are not equivalent, meaning non-collapsible, when there exists a string Z such that the path of Z from P goes to a final state and the path of Z from Q goes to a non-final state. Now there may be a little confusion. Maybe we can try to understand what it is. How is it related to these two? This statement is not considering this crossed part. From the second, it is not considering the both final, both non-final case, and it is not considering the first statement. Then is it correct? Consider a situation. So the first statement is looking at this kind of a situation where two states P and Q are reachable and one of them is final and the other one is non-final. Then the question is, how is it that this statement can handle this situation? So you just take the string Z as epsilon in this equation. That means the path from P for the string epsilon is P itself. From P, if you are not processing any simple, you are in P itself. It is a final state. And the path for the path for epsilon from Q, the same string epsilon from Q, ends in Q itself, and which is a non-final state. So that means this is enough. Here you can see that epsilon is a string witnessing the non-equivalence of P and Q. So if you want to establish that P and Q are non-equivalent, then you want to find a string witnessing their non-equivalence. Witnessing means that string will take you to final state from one of them and to a non-final state from the other, and that is the witnessing string. I think it is clear. So this statement is enough, and you see that both final or both non-final, that is not required because this is a very generic statement. And the only other case is the first one. The first one is anyway handled by taking Z as epsilon. And now you consider both as final or both as non-final. Then Z will be a non-empty string. That is the only case. Think about it if you are not able to follow. Anyway, let us proceed to the next. So the question is, how can you find states which are non-equivalent, and that is what we found, and maybe we can try to understand it by rewriting it in a simple term. If the states P and Q are not equivalent, then we need to find a string Z witnessing the non-equivalence of P and Q. Just like this, in this case, epsilon is the string witnessing the non-equivalence. And in this case, Z is the string witnessing the non-equivalence. So we need to find a string Z which witnesses the non-equivalence of P and Q. And if that is the case, if there exists a string Z distinguishing P and Q, then the claim is that there exists a string with the length at most L. Is because suppose these are non-equivalent. Why they are non-equivalent? By this definition, there exists a string Z such that the path for Z is going to final state from P and non-final state from Q. Then from the non-fact about graphs, that n minus 1 is the maximum length of an acyclic path in a graph with n vertices. We know that the length of Z can be bounded by the number of states in the DFA. Hope you followed it, otherwise please watch it again and see what is going on. So what we found is that two states are non-equivalent if there exists a string witnessing their non-equivalence. That is a string which will take you from one of them to a final state and from the other to a non-final state. So we need to write the algorithm. We are going to the algorithm now. The algorithm needs to mark pair of states as equivalent or non-equivalent. And to mark a pair of states PQ as non-equivalent, the algorithm need to find a string Z witnessing the non-equivalence of P and Q. And that's it. So here is the first step of the algorithm. Mark a pair of state PQ as non-equivalent if one of them is a final state and the other one is a non-final state. I think you agree that yes, in fact, then they are non-equivalent. Anyway, we can, because there exists epsilon as the witnessing string for non-equivalence of P and Q. Because if P is final, assume that P is final, then from P, epsilon is taking you back to P, which is a final state. And Q is non-final state, epsilon is taking you back to Q only, which is a non-final state, and that is it. And the second step in the algorithm is a loop. You have to perform this step in a loop until you find no more pairs to be marked. What you do is, suppose that there exists a pair of state not marked. That is a state, maybe I can explain with the help of a figure. Suppose PQ is a pair which is not marked. And on A, from P you are going into R. And on A, from Q, you are going into S. That is the case. PQ is not marked as non-equivalent, but RS is marked. That is what I said. Okay. I said, what is R? R is nothing but delta PA. That is delta PA is R. And delta QA is S. So I said, if delta PA, delta QA, that is the states to which you will reach from P and Q on A, that is RS. If that is RS is marked and PQ is not marked, then the claim is that you can mark PQ as well. Is that correct? If this is the case, if RS is marked, why is it marked? There exists a string Z witnessing the non-equivalence of R and S. That is, from R, you are going to a final state, and from S, you are going to a non-final state. If that is the case, then you can see that AZ is the string witnessing the non-equivalence of P and Q, because AZ will take you to a final state from P, and the same AZ will take you to a non-final state from Q. So that's the case. So this algorithm step is correct. If you have PQ as unmarked and on A you are reaching into the pair RS from PQ and RS is marked, then you can mark PQ as well. So that's the algorithm. These are the only two steps in the algorithm, and step 2 is in a loop. You may look it as like an infinite loop, but later we will see that it is not infinite, it's a finite loop only. That we will do later. Okay, now we can try to apply the algorithm on an example. So here is a DFA given, and we need to find all pairs of state. These are the possible pairs. 25 pairs are there. Q0 to Q5 are the states. So these are all the pairs. We need to mark them as non-equivalent. So what is the first step? Mark a pair of state PQ as non-equivalent if one of them is final and the other one is non-final. So this is the first step. You can see that Q0, Q1 is marked. Q0, Q1 is marked because one of them is final and the other one is non-final. It's symmetric, therefore Q1, Q0 will also be marked. Q1, Q0. So this is symmetric. Actually, no need to find both the triangular portions. Only one is enough, but I am showing both. Okay, you can just verify that it is correct. Maybe we can verify the first row. Q0, Q1 you can mark because one is final and one is non-final. Similarly, Q0, Q3 is there. Q3. And only other case is Q0, Q5. No other marking. So this is exactly what we did. You can verify it offline. So this is the step 1. Now you perform. Step 1 is to be performed only once. Now step 2 in a block, in a loop. What is step 2? Step 2 tells that if a pair of state is PQ is not marked and delta PA, delta QA is not, if PQ is not marked and delta PA, delta QA, that means the state to which you move for A from P and Q is marked, then you can mark that pair. Please don't confuse. Maybe we can try to understand why is it that Q5, Q1 is marked. In the previous case, Q5, Q1 was not marked. Okay. And but we can see that maybe Q0, Q5. Okay, now you consider, suppose Q1, Q5, you are in Q1, Q5. For A, where are you going? From Q1 you are going into Q2. And from Q5 you are going back to Q5 itself. So you are getting Q2, Q5. I think Q2, Q5 is marked here. Yes, Q2, Q5 is marked here. Okay, you can see that Q2, Q5, this is the state marked. And hence, because from Q1 on A you are going to Q2. And from Q5 on A you are going to Q5. And therefore you can mark Q1, Q5 using the second rule. Okay, don't worry about it if you are not able to see it now. You check it offline, you can see that it's correct. And just look at the statement of the algorithm and execute it. That's what you do. And this is the first pass of the second state. And one more path you can go. The second time when you execute the same step, you are making more marking. Third time, you are not getting any more mark. That means no more pairs can be marked and you are finishing here. That is no additional marks and hence the algorithm stops. And this is the set of all pairs of non-equivalent state. Okay, this is the set of all states, pairs of non-equivalent states. This is a symmetric matrix and hence no need to find both triangular position. Finding a lower triangular position or upper triangular position is enough. The other one is just the mirror image of this because it's a symmetric relation or a symmetric matrix. Okay, so two states P and Q are not equivalent if there exists a string Z witnessing their non-equivalence. A pair of state is, that means if this algorithm leaves a pair of states as unmarked like Q4 and Q2, that means they are equivalent. So equivalent pairs are those pairs left unmarked by the algorithm. Okay, here are the equivalent pairs. You just see the equivalent pairs. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They are equivalent pairs. That is Q0, Q0, then Q1, 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 Q3, Q2, 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 Q4, etc. It goes. And there is a nice thing, you can see that this set of pairs, which is a subset of the Cartesian product Q cross Q, you can see that this is an equivalence relation. It's a very nice observation. So why is it that it's an equivalence relation? Quickly verify that it is a reflexive relation, because Q0, Q0, Q1, Q1, Q2, Q2, Q3, Q3, Q4, Q4, and Q5, Q5 are there. And it is symmetric, because Q1, Q3, Q3, Q1, Q2, Q4, Q4, Q2. It's transitive also. Q1, 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 Q3, you need to have Q1, Q3, it is there. And what is this? Q1, Q3, Q3, Q1, you need to have Q1, Q1, it's there. Q1, Q3, 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 you need to have Q1, Q3, it is there. Q2, 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 Q4, so you need to have Q2, Q4, it is there. And now Q2, Q4 and Q4, Q2 requires you to have Q2, Q2, which is there. And maybe the last pair, Q2, Q4, 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 you need to have Q2, Q4, which is this itself. So it is transitive also. So you can see that the equivalence relation that we found, the relation that we found between two states is in fact an equivalence relation. We will formalize it later, and that's it. Now collapsing. This is the set of equivalent states that we found. We need to collapse. See that these are same states. Q0 and Q0 are equivalent. Qi and Qi are equivalent for all I. So no need to collapse. Collapsing means the same state, Q0 and Q0, nothing to do. It's an idle thing, identity operation. Q0 and Q0 collapsing is nothing. So no need to do anything, all these are collapsed. Not that this is Q0, Q0, Q1, Q1, Q2, Q2, Q3, Q3, Q4, Q4 and Q5, Q5. Collapsing, you don't have to do anything. And the next pair of states to be collapsed is Q2, Q4, these two states, and Q4, Q2, these two states. How will you collapse it? Collapsing means you make a single state from Q2 and Q4, and all the four transitions coming to this, that is for A and B, should come to the collapsed state Q2, Q4, and a single edge should go out to the next state, and that is what you do. Okay, you can see what exactly is done. When you collapse, what you do is merge these two into a single state and redirect all these edges to that single state. That's it. And now the next pair of states to be collapsed is Q1 and Q3. Q1, Q3, Q3, Q1. Do the same, you will get this machine. And this is exactly what we got, and this is the unique minimal automaton, which is now obtained using an algorithm. And if you practice it for more example, it will be clear, and only then it will be clear to you. Okay, and the nice thing is that the states of the resulting automaton is nothing but the equivalence classes of this equivalence relation. You just see what are the equivalence classes. Here only one is there in the equivalence class of Q0. It is only related to itself. These two are related. This is the other equivalence class. This is the third equivalence class. And this is the fourth equivalence class. So the states are going to be the equivalence classes of the equivalence classes of the equivalence relation that we found. Don't worry, we are going to formalize it. The equivalence relation on the state set of a DFA. Let this be a relation on the state set Q of a DFA A such that when P and Q are related, if for all strings Z, regardless of what string you take, the path for Z from P goes to a final state, if and only if the path for Z from Q will also go to a final state. In other ways, you cannot find a single string Z such that Z can witness the non-equivalence of P and Q. That means they are equivalent. For all string Z, if the path of Z from Q goes to a final state, then from P also it must go to a finite state and vice versa. And you can verify that this relation is reflexive, symmetric, and transitive, and hence an equivalence relation. And the nice thing about this relation is that the minimal state automaton B, which can be obtained from an arbitrary automaton A directly from the equivalence from this equivalence relation, and that construction is what is called quotient construction. I will give you it quickly here. The equivalence classes of this relation is going to become the state set of B. That is exactly what we did in a different way. And the start state is nothing but the equivalence class of small s, which is the start state of the automaton A. And what are the transitions? The transitions are this. Equivalence states are going to be, equivalence classes are going to be the states. From the state represented by the equivalence class P on A, the transition should go to the equivalence class of the state to which you can reach from P on A in the given automaton. Okay, you need to read it carefully and see what it is. And finite states are the set of equivalence classes said that F is a finite state in the given automaton A. If you are interested in, you can try to read it and understand, otherwise just leave it, because for the examination point of view, this may not be there. But this is exactly what we did using the algorithm. The algorithm is actually simple to apply. And with this, let me move on to the last part where I am giving you assignment. The first one, apply the state minimization algorithm on this DFA, obtain the resulting DFA, and observe that the states of the resulting DFA are the equivalence classes of this state set. And one more, apply the state minimization algorithm for this automaton. This is what we obtained by NFA to DFA conversion, that is discussed in the last but one class. And so in this lecture we have seen the state minimization algorithm for DFA. Thank you.